So I'd like to finish off this unit with a couple of videos just reviewing the big concepts that we learned in graphing for Math 10. And the first big concept is how do you analyze a graph? In other words, describe exactly what the graph is showing you. And there's some fair number of words involved in it. I've listed them on the left, and I'm just going to work through each one. And you'll notice and probably recognize this is taken from a screenshot of the Graphing Stories website that we visited in class, and you can practice that as well by going to the link that you have on my website. So let's get started. You'll notice when you look at this graph for the first time, it's got a title. It'll say distance from home plate. And so here we have the vertical axis, or the y-axis. The units are feet. Look, notice the scale has to be the same. We're going up by 12s. And the horizontal, or x-axis, is time. It's in seconds, and you'll notice it here. So our first description is discrete versus continuous. And you have to ask yourself, when you measure in seconds or when you measure in feet, can you have a partial unit? Could you have 2.5 feet or 2.1 feet? Or could you measure time in fractions of seconds? Another way of thinking of it would be when you're watching someone run around the home plate in the diamond, do you see them appearing and disappearing each time, or is it one continuous movement? And finally, in this particular case, they've graphed the distance from home plate, and you can see that we have a solid line. So all of this information suggests that this is a continuous function. You should also be aware that another way of knowing that if it's a continuous function is if you're given the equation. Now in this case we're not given the equation, but we can tell by thinking about the units, thinking about what we're measuring, that fractions and decimals are allowed. Therefore we connect the points, and this is an example of a continuous function. A discrete function would be a series of separate points. They could be linear, they could be nonlinear, but you would not connect the points. The next idea is linear versus nonlinear. Excuse me. And you'll notice if you look at this graph that you've got really 4 parts, each of them on their own are linear. So how do you know if something's linear? When we look at a function to tell if it's linear or not, we actually have to look, for example, at this first piece, we have to look at what's called the rate of change, or the slope. The rate of change, or the slope, has to do with, and in this particular case, let's look at the rate of change between 0 and 3 seconds. So between 0 and 3 seconds, yes, it's one straight line, but mathematically we would say that the slope of this line, we use the letter m for slope, has a rise of 72, and I'm going to write down the units, feet, over a run of 3 seconds. If we divide those, we get 24. Notice if you actually write down the units, you can see what rate of change or slope represents. 24 feet per second. And of course feet per second would be speed. That's how fast the person is running from home plate to first base. You'll notice the next line, this person slows down. How can I tell? Well, the graph is less steep. Also, though, we could calculate its steepness, and you would find that that number is smaller than 24. I'm going to save the next calculation, though, for the final piece. If you look now at the final seconds, you'll notice that here we have another graph. This is where they're going from third plate back to home. And you'll notice, and I wanted to use this example, because now when you go to calculate the slope, you'll see that in the 4th section you are dropping. You're going down 72 for a run of 1, 2, 3, 4. So this is going to be a negative rise because the line is going down. The run is still positive, 4 seconds. If we divide those, we get negative 18, and remember the units are feet per second. And so that's how you can tell if it's a linear function or not. Now, I've used this example to show that this graph is 4 different lines. Each, I can tell, has a different slope. So therefore, technically, overall, because this graph doesn't have one line with one slope, we're going to say that this is a nonlinear function. Let's now talk about domain. First, let's do some definitions. Domain would be the possible, or the set of possible x-coordinates. If it's discrete, you would just simply list all the x-coordinates. They might be 0, 1, 2, 3, whatever they are. But in a continuous example, like here, we can't list all the x-coordinates, because even if you think it's just 0, 1, 2, 3, up to 15, you're forgetting that this is continuous, therefore decimals, fractions are allowed. And of course, if we were to split time in continually, you're going to get an infinite number of decimals, fractions. And so we want to say that the possible x-coordinates for this graph, in other words the domain, is between 0 and 15 seconds, inclusive, which means the points at 0 and 15 do exist. But we use mathematical symbols for this. We start with the lowest value for x. We write down what we're looking for, which are the x-coordinates. We end with the highest value of x. And because we're in order, we use less than symbols. The equal sign is the inclusive part. 0 and 15 are actual points. That's how we write down between 0 and 15 seconds mathematically. That's domain. Range would then be the possible, or the set of possible y-coordinates. Take a look into to figure out if you can think what the range would be of this. What would be the smallest y value? What would be the highest or the largest y value? The largest y value. Now you'll see the largest y value is way up at the peak here. It occurs around 7 seconds. It's kind of hard to tell with this scale what it is. So it's between 108 and 120, a little closer to 120. Why don't we say 115? We're just estimating. Again, this is how we write down mathematically between 0 and 115 feet, less than or equal to, always when we're putting it in order from left to right. So that is, where are we here? Domain and range. Let's talk about now the intercepts. So an intercept is where there is an intersection, just like the intersection of two roads, but in this case the x-intercept is where your graph or your function touches or crosses the x-axis. And you can tell here and here, in other words, at 0 and 15 seconds, this person has a height of 0. So we'll say that the x-intercepts, and there's two of them here, are 0, 0, and 15, 0. What's important to notice is that the x-intercept always has a y-coordinate of 0. And that's because, of course, it's on the x-axis. If we're looking for the y-intercept, we're now looking at the y-axis, which is here. And if you look at the y-axis, we really only have one point. And that's our starting point. And that's 0, 0. And again, you see a pattern. The y-intercept occurs when the other measurement, in this case the y-coordinate, is 0. That's intercepts. Finally, functions. A function is best, almost easier to describe when you have something that is not a function. So a common mistake a lot of students make when they analyze a particular graph, they forget what they're measuring. Let's say we took the shape of a baseball diamond, and if we measured the person's distance away from the plate, this of course is what we got, and this is the graph we're analyzing. The mistake some students make is they do this kind of rational thinking. They think, okay, you're running away, and now you're running closer to, so they physically draw out the path of the person, but we actually want to measure their distance from the plate. So what I've just drawn is a good example of something that we would say is not a function. In other words, what I've just drawn is really not possible if you're measuring time and distance. So for example, let's say after 3 seconds, it would make absolutely no sense for someone to be, I don't know, 30 feet from home plate and to also exactly the same time be 60 feet from home plate. That just doesn't make sense. You can't be two places at once. In other words, you can't have two different y coordinates when you have the same x coordinate. So if you see a situation where your points are in a vertical line, this is called the vertical line test. And it means this is not a function. Again, if I wrote down the points 330 and 360, when we had a time of 3, if you've got two different values, that is not a measurement that would be possible when you're measuring distance and time. In this particular case, going back to our graph, we don't have that situation. So yes, this is a function. And finally, if you want to practice interpreting some graphs on your own, interpreting graphs is simply thinking of a real-life situation and drawing what that situation looks like on a grid. I would recommend visiting Graphing Stories. You can Google it, go to my website, do a little bit of practice, and then also review the concepts that we talked about today. And that's our first big idea. What's a graph? How can we read a graph? What are some of the descriptions that we use for graphs?